Okay, good afternoon, everyone. We will continue our discussion. So last week was very short in the sense we did not cover much ground. So let's use this particular session to cover the optimization methods. So let's recap what all things we have covered till now. So till now we have covered the different types of analytical methods. So in the analytical methods, for single variables, the one which was already known to you, that is f dash x equal to 0. We said that how it can be extended for multi-variable types, and here we are talking about unconstrained. So that means constraints are not there. So in that case, we introduced the concept of, can somebody tell what is this, what are those two things? Multivariable analytical approach. The terms which are highlighted here. So what are those terms called?
Hessian matrix.
One is Hessian matrix, and the first one is, this is the Hessian matrix. And is del of x is
Gradient.
it's a gradient, that's right. So for a given function, if you have a function known, then you can calculate of multiple variables. You can calculate the gradient and Hessian matrix, and based on the nature of Hessian matrix, you can determine the necessary condition is that the gradient should be 0, and sufficient condition is that Hessian matrix should be positive definite. Next, we move to the constraint optimization problems. So in the constraint optimization problems, we talked about first equality type of constraints, and in that we developed something, this L function. So anybody can tell what is this L function stands for? So it's a Lagrangian function. So this method is called as a Lagrangian multipliers. So these VIs are all Lagrangian multipliers. So each of the equality constraint function gets multiplied by its own Lagrangian multiplier, and you form a unconstrained problem and then solve using the same method that we discussed previously. And in case of inequality constraints, that is both equality and inequality constraints, we have seen that this method is also based on Lagrangian function, but there are some additional conditions which are required. So anybody remembers what is the name of that condition which we use in inequality constraints? It is acronym with 3 letters.
KKT.
Yeah, that's right. So we use KKT conditions, Karush-Kuhn-Tucker condition. That is what we use. So this is what we covered last week. Last week we started discussing about the numerical methods, and we discussed single variable numerical methods. In our tutorial part, we have already covered a method. So in single variable methods, you have methods which are covering the bracketing methods. That is, they rapidly find out what is the window within which the minima would lie. And there are many methods, out of which we have seen in the tutorial the exhaustive search method. And the last lecture, only thing which we covered is a single method, which is again belonging to single variable type, and it is called as a golden section method. So these methods are called as the golden section method, and the other methods in that family which we did not cover are called as a direct search method, as against another family of methods which is known as gradient based methods. So can somebody tell what is the difference between direct search and gradient search method? The name gradient search itself is a big hint. So
So in the direct method, we don't calculate the slope.
That's right. So so what we use there?
Only the equation of the function.
That's right. So we have to only calculate the value of function in direct search methods, whereas in gradient based method, which we are going to cover today, we need to calculate the slope, either first derivative or the higher derivatives depending on the method. So in this course, we are covering only first derivative method, simpler methods, but certain methods in gradient base require the higher order derivatives as well. Okay, so that is what, so we'll be covering for single variables, the direct single variable we have covered direct gradient, direct search method, and we will be today looking at gradient based method, which is already you might have come across. And then we'll move to the multiple variable methods. So in multiple variable methods, we are going to try to cover three types of methods, and that is what we are going to cover today. So let's move to the gradient based methods. Gradient based methods, as the name suggests, would require calculation of gradient or derivative of the function. Only here we are talking about numerical methods, so we'll be calculating the derivative numerically. So the method, again in gradient based method, there are different types of method with the advantages of each. So the method that we are going to cover in this course is called as a bisection method. So maybe in some mathematics course or some otherwise you might have come across this method, but we'll nevertheless see it again. So the logic of this method is as follows. So we are again talking here of single variable functions. So we are not yet got in multivariable, but multivariable, the same concept. We'll see how to apply it in multivariable. So we have a function which is having some minima in the range which is given. So this is the function, and we have established two of the limits within which the minima lies. So to begin with, we require 2 points, A and B, and these points should be such that at point A, the slope should be negative. So here we require f dash x negative, and at the other point, we require f dash x positive. So if that is the case, then only we can begin with this particular method. Once you arrive at this particular point, what we do next, as the name bisection suggests, we will bisect the interval a to b into half. So we'll consider the midpoint of this particular section. So this function I have drawn is symmetric. So let me just make it unsymmetric so that we have some. So let's say the minima lies somewhere away from the center, otherwise we'll have okay, so I'll say that minima lies somewhere there. And not exactly at the center. So here the slope is greater than 0 and other place it is smaller than 0. Okay, so first step is to bisect this interval into half. Yeah, so just forcibly shifted the minima to away from the center. Now at the midpoint, so whatever new point that you have formulated now, so you have to find out slope of the function at this particular point C, and depending on this slope of this point, you have to take a decision. So slope at this new point. So the slope at new point, if let's f dash c, if it is greater than 0, if it is less than 0, or if it is equal to 0, then we have to take a decision about what to do next. So I think by common sense you should be able to tell what should be done. So let's take first the case where slope is 0. So what is the conclusion?
Minima would lie.
So that will be minima.
That would be minima. So this part is clear. So this indicates that it is minima. Now let's consider the slope is less than 0 as the figure I have drawn. If the slope is less than 0, then what to do?
We would have to move forward as the minima would lie ahead.
Okay, so what is the new interval within which we have to search now? So earlier it was A to B was the interval what we were searching. Now in this particular case, so let me just change the color. So if this is the case, so what is the interval for less than 0 case?
It will be B to C.
It will be B to C. So now if this is the case, then we will have the interval which is B to C. And the third case where the slope is greater than 0. So here it is C to B is the, or B to C is the interval. And if it is greater than 0,
Then A to C.
then it is A to C. So that is how this particular algorithm works. So as simple as that. So you choose 2 points such that the slope changes from negative to positive from one point to the other point. And then you start taking midpoints, and depending on the slope at the midpoint, you decide which region to eliminate. So it is essentially a region elimination method, but based on the gradients, not based on the values. Okay, so that is the concept, and let's write down the algorithm so that it can be converted into code form. So any other question or any other situation which can arrive here? So
So
under which,
like
yeah,
if we are using this method, like
yeah,
can't we say that you have to go towards one side, like go towards any side till you get a slope 0 and then stop over there?
yeah, that I mean, so within gradient, I don't know whether the method what you talked, whether it exists or no, but it appears to be yeah, commonsensical, in the sense there must be a family or one branch of these methods which does like that. So we keep on searching slope till the time it becomes 0.
Yeah, like I'm not saying to go on the right side, just staying on the left hand side of the graph. Just keep on go down down till you get the slope 0. Once you
Okay.
get it, stop over there.
Okay. So what interval you will take for your step? So here we are talking about numerical method. So you have to write the algorithm such that it works. So for example, your method can become tricky, or in the sense it becomes lengthy if your range is something like this. So if you decide to go from here, then you will require many steps to reach the 0 point.
Yeah.
I'm just discussing my doubts as to your method. So then you will say that once I will go from this side and once I will go from that side. So that is somewhat better algorithm.
Okay.
So I'm sure there must be some method based on this algorithm. If it is not, then you publish your method and get it named after you. Okay. Okay, so that is the gradient belt method. Means in the book you will find some more methods in addition to bisection method, and they are in a sense more powerful than this method in certain situations. So this method advantage is that you are taking cognizance of both sides of your range, and you are hitting at the middle, hoping that the range is symmetric and the minima lies at the center. So the convergence would be is likely to be faster in certain situations. Again, this requires that you require the minima to be single, means there is only one minima between the range. If there are multiple minima, it may capture only one of these. Yeah, that's right. Okay, so I'm just writing the steps so that this algorithm can be converted into program. So in the algorithm form. So essentially, whatever we discuss now, I'm just writing it in the form so that program it can be converted easily into a program, computer program. So choose the essential part. First is choose 2 points. So how to choose these 2 points could be based on the bracketing methods A and B, such that f dash x is less than 0, f dash a is less than 0, and f dash b is greater than 0. And also choose, so we require some limiting conditions. So we choose a small number. So this is the termination criteria epsilon. Okay, then you calculate x1 equal to a, and means you denote x1 as a and x2 as b. Okay, step 2. So at this stage, I want to ask, this condition we have written f dash a less than 0 and f dash b greater than 0. Will this method work if it is other way, that is f dash a is greater than 0 and f dash b is smaller than 0?
Like in that case, there will be a maxima, I
That's
guess.
right. Yeah, that's good. So it will, in that case, we will not be identifying minima, but we will be identifying maxima. That's right. Okay, then how do I calculate the slope? Since we are in the numerical method, we have already discussed, I think in the some previous class, how to calculate the slope numerically. So we'll use the basic definition of the derivative to calculate the slope. So f dash x can be calculated as at any point with at x1, x2, or the further midpoints when we have to calculate. The f dash x would be calculated by the basic definition. So it is x plus h, or x plus delta x minus f of x divided by delta x. So that is the method what we learnt in the basic definition of the derivative. So limiting delta x tends to 0 will give you the value of slope. So when you are numerically calculating the derivative, you have to write a code which will calculate the derivative of your function based on the two values at x and x plus delta x. How much delta x to be taken, that depends on your judgment or the nature of your function. Typically, the delta x is taken as 0.01, that is 1% of x. This is again a thumb rule, not hard and fast. So depending on your problem, you can vary that. This way of calculating the derivatives, so that is known as finite difference method. So using this, you can calculate, and the method, the formula what we have wrote here, that is known as a forward difference method. There is another backward difference method, and there is known as central difference method. In most of the problems, the central difference method is found to be more better prediction of the slope at a particular point. So the central difference method, the f dash x is calculated as, so instead of going forward, so you are considering only function value at forward point and the function value at the instantaneous point. So here you go one step ahead. So f of x plus delta x minus f of x minus delta x. So don't calculate the value of function at the instant where you are there, but you can go one step ahead and you go one step behind and divided by 2 delta x. So this is known as central difference method. And this method is typically used in all numerical methods for calculation of the derivatives. And there are formulae for calculating higher derivatives based on forward difference, backward difference, and central difference methods. So that you can find in any book of mathematics or the numerical methods. So our method doesn't require higher derivatives, but there are formulae for f double dash x, f means any higher f nth x can be found out by the numerical method, and the formula exists for that. Okay, so when you are writing code for this, you have to calculate derivative of the function. So derivative of function, we are assuming that we are not going to use any analytical function for derivative. So we'll be using the numerical derivative method, and it is recommended to use the central difference method. No harm if you use the forward difference method, but the central difference method is something which is recommended. Okay, so now once we have done this, then we have to calculate the midpoint. So midpoint here I am writing as z. So that is x1 plus x2 by 2, and evaluate the derivative at z. F dash at z. And step 3 is where you are evaluating. So if the absolute value of derivative, if it is less than or equal to epsilon, then terminate. That means the z is minima. Else if f dash of z is less than 0, then set x1 equal to z and go to step 2. And if it is greater than 0, f dash z, then set x2 equal to z and go to step 2. So this is the same thing what we discussed here. If it is negative, then you are taking the forward side, and if it is greater than 0, then you are taking the backward side. Okay, so let's take one numerical example which illustrates this thing. So we'll use the same function, minimize fx equal to x square plus 54 by x. So we already know that this particular point has got minima at x equal to 3. So where we have been given the range a equal to 2 and b equal to 5. So within 2 and 5, we know that minima lies, and epsilon is given, that is the termination condition is given as 0.001. So step 1, so we have to calculate the step at these 2 points. So f dash a equal to, so we require f of x plus h. So it is 2 plus, I'm considering delta x as 1% of x. So that is 0.02 minus f of 2 minus 0.02 divided by 2 into 0.02. So this will be minus 9.501, and f dash of b would be f of, so here it will be 5.0. Okay, so here in the second part, it should, I have taken this delta x for both these conditions as 0.02, which is the 1% of the smaller number. So here I have not considered 0.05, I have taken it same. minus f of 4.98 divided by 2 into 0.02. So this is plus 7.84. So I verified that at the left point it is negative slope and at right point it is positive slope. Then step 2. So we'll take z as x1 plus x2 by 2. So that will be equal to 3.5. And we'll evaluate f dash of z. So that is f of 3.535 minus f of 3.465 divided by 2 into 0.035. So slope comes as plus 2.591. So we are getting the positive slope. So since f dash of z is greater than 0, this implies x1 equal to so much and x2 equal to so much. So now we have to decide the new range. So we started with initial x1 was 2 and initial x2 was 5. And now we have evaluated at 3.5 and the slope is positive. So that means the range should be what to what?
2 to 3.5.
It should be 2 to 3.5. So it should be always negative on the left side and positive on the right side. So it is 2.0 to 3.5. So this process you have to continue till the time the termination condition is met, till the time you get the slope value which is less than the termination condition. So obviously doing that manually doesn't make any sense. But if you continue like that, you will find that you will get the solution. Okay, so we have covered the single variable function methods. Now why we are looking into single variable functions is because the multivariable functions can be converted into a single variable function, as we will see in the next session. So we have seen that single variable functions, we have seen two methods. One is a direct search method, that is a golden section method, which we covered previously, and we have seen gradient based method, which is the bisection method, which we have seen just now. Now any of this method can be used for multivariable function, not directly, but in a way which I am going to discuss now. So now we will discuss the multivariable optimization. So multivariate optimization. So in this again there are different algorithms are there. The first one we will discuss is how in one of the approach we can convert the multivariate problem into a univariate problem or single variable problem by a method which I will explain now. The method that we are talking here is converts the multivariate problem into a univariate problem, and the common name for this family of approach is known as unidirectional search. So as the name suggests here, in this method you have to decide the starting point of your search. So you are searching for the minima. So once you decide the starting point, you have to also decide in which direction you are going to search. So for example, you are having a function of two variables. So just to visualize it is simpler. So it is x1 and x2, and our function is let's take The objective function is a circular function where minima lies at this particular point. So this is the optimum point, and these are the contours of the objective function. So objective function keeps on increasing circularly about this particular point. So your objective function fx bar will be equal to something x1 minus a whole square plus x2 minus b whole square. Okay, so the minima lies at a and b. So in this case, the method that we are going to talk, unidirectional search, it converts this particular problem into that of a single variable. The way we do it is as follows. So we select any point. So this point is based on the judgment of, or it may be chosen randomly as well. So that is the starting point. So this starting point you are chosen. And you have to also choose the direction in which you want to move. So you'll be choosing two things. One is the starting point, another is the direction in which you have to search. How to search, how to select this direction is, we'll see later. It can be, there can be some approach by which you can choose a better direction than the other. But this also could be random. The starting point also could be random. The search direction also could be random. Basically in the problems which are having multiple minima, the random approach would work better. But in problems such as this, a fixed direction based on certain calculus based method would be a better strategy. So depending on problem to problem, the search direction as well as the starting point location can be done either randomly or based on some calculations. So having decided these two parameters, then we can convert this multivariable problem into that of single variable problem. So how to do that, I will just explain now. So this particular starting point, so I'm just writing, let the starting point be x bar t and starting direction or the search direction be s bar t. This t indicates the iteration number. So t is the iteration number. So on tth iteration, you have the starting point as given x bar t. Why bar here? Because it is a multivariable function. So this particular point will have some coordinates x1, x2. So that is nothing but the x bar. And for a certain iteration, so it is a tth iteration. So that is why the t is coming here. And similarly, the direction would be in terms of direction cosines of the search direction. So along means you have multiple dimensions oriented in x1, x2, x3. So in that multi-dimensional space, in x1 direction, how much you want to move, in x2 direction, how much you want to move, that will define the search direction. In two-dimensional or three-dimensional scenario, you can imagine them to be like direction cosines of that particular vector. In higher dimensions, it could be similar vector having a unit magnitude. Okay, so having defined this starting point and orientation vector, what can be done is that any point which is lying on this search direction. So if I choose any point which is lying on this particular search direction. So if this is any point which I want to locate on this particular search direction, it can be written in terms of parameter alpha, where alpha is the distance between the new point and the old point. So we can write this, if you introduce one more parameter alpha, then, and this point as x bar t, any point along the search orientation, then x bar t could be written as follows. So x bar t would be given as, sorry, x bar at tth iteration at a distance alpha can be written as x bar t, that is a starting point, plus alpha times s bar t. So a point which is lying along this direction can be written in terms of a single unknown parameter alpha and the known starting point and known search direction. So in this expression, any point on this search direction can be represented only in terms of single unknown, and that is alpha. So here, note that this x bar t is a set of numbers and s bar t is also a set of numbers. So alpha is the only variable. That means any point along this direction can be written in terms of a single variable alpha. And once you substitute these values into your main function, this function would become a function of only single variable alpha. So that is the logic we will use. So any function can be converted into that of that consisting of unknown alpha, where alpha is a scalar quantity or simply a number specifying the relative distance of x bar t alpha from x bar t. And the objective function fx bar can be rewritten in terms of alpha using equation 1. So I'm calling this as equation 1. So using this equation, your original function, which is multiple variable, can become a function of only alpha. And now this f of alpha can be minimized using the univariate methods. So you may use a golden section method or you may use bisection method to calculate the minima. But note that the minima here would not be your final minima. So for example, in this circular type of objective function, if you had chosen the uh, search direction as shown here, the minima you will obtain by this method is not the true minima. So the minima what you obtain here is where this line become tangent to the circle. So in this kth iteration, you will find the minima which is this point, which is away from the global minima. So global minima is here, but whereas along the direction that way S bar you are searched, you reach to a point which is not actual minima, but it is closer to minima than where you started with. So in this method, the next iteration, you will take the new minima as the new starting point. So x bar t plus 1 would be equal to the minima that we have found in the previous iteration. So in this way, you will proceed. So again, with this as a starting point, you will choose another search direction and you will reach another candidate for minima and so on. And hopefully you will reach to the minima in a reasonable number of iterations. So that is how this particular method works. So this is known as unidirectional search method. So we'll quickly have an example which illustrates this particular method. So I have not written here, but the next step is, so f dash x, f dash alpha can be minimized along the using any univariate method. The new the minima found at this iteration will be new starting point for next iteration. Which means that x bar x, x, x dash t plus 1 would be equal to x bar whatever alpha star that we have found out, where alpha star is the minima, alpha corresponding to minima. And then you have to choose another s bar t plus 1 and proceed with your iteration. Okay, so let's take one example which will make this procedure, consolidate the understanding of this procedure, and then we'll discuss if you have any questions. Minima is f of x1 x2 equal to x1 minus 10 the whole square. So this is a circular optimization problem, x2 minus 10 the whole square. So we already know the minima of this is at x1 equal to 10 and x2 equal to 10, with x bar t, the starting point, as 2, 1, and search direction as 2, 5. So note that here, although I said that this s bar t is a unit vector, it need not be a unit vector. So for this method to work, this need not have, this s bar t need not be the direction cosines along that particular vector direction, or the magnitude of this s bar t could be anything, because here we are talking in terms of the relative distance from the point x bar t. If it is a direction cosine, then you will get the exact distance, but if it is otherwise, then alpha will be some multiple of the real distance between the point along that line and the starting point. So so that point, just note it down that this is not a unit vector, and that is okay. For this method to work, you need not have unit vector as the search direction. So only the proportion, when x changes by 2 units, the y changes by 5 units. So that is what we are looking at. So this problem, what we are doing is like this. So we are having minima at 10, 10. So this is 10, 10, and our objective function is increasing away from this point, and we are starting at point 1, 2. So 1, 2 would lie somewhere here. So this is our starting point, and we are moving in a direction which is having slope 5 is to 2. So 5 is to 2 would be something of this type. So this would be our search direction, S bar t, where this is 5 is to 2. The slope of this line is 5 is to 2. Okay, so we have to, what we have to do here is we have to convert this f of x1, x2 into that of alpha. So for that you have to define the x bar t. So we'll use the function x bar t alpha equal to x bar t plus alpha times s of t, s bar of t. So this would mean that x bar is 2, 1. So this is 2, 1 plus alpha times 2, 5. So which makes it, so on the left hand side you have x1, x2. This will be 2 plus 2 alpha, and this is 1 plus 5 alpha. So we have to substitute this in our function. So our function is f of x1, x2 is x1 minus 10 whole square plus x2 minus 10 whole square. So we have to substitute here x1 as 2 plus 2 alpha minus 10 the whole square, and this is 1 plus 5 alpha minus 10 the whole square. So our function becomes 2 alpha minus 8 the whole square plus 5 alpha minus 9 the whole square. So that becomes our function. So we have to find minima of this function in terms of alpha. So that will tell us that along this direction, wherever is the minimum, so that is the candidate point for starting the new search for the next iteration. So is this clear what we had? So that is the key for this algorithm. The rest is just arithmetic. So any questions or any doubts at this stage?
Sir, I have a doubt.
Yeah.
Sir, is x bar t constant or is it variable? Like, is it
X
any
bar,
randomly chosen variable?
usually it is randomly chosen unless you know the nature of your problem. It's where the minima is likely to be. So we'll choose some point which is nearby to that particular point. Of course, in a real problem, you just have feel that the optimum production will take place when this machine works more and this machine works less. So appropriately, you can choose your starting point.
Okay, sir. Sir, and what if there are more than two variables?
Yeah, the same logic would work, no? So if you have here plus x3 minus 10 square plus x4 minus 10 square, the same thing will work. You have to choose the starting point in terms of maybe 1, 2, 3, 4, and direction again, whatever.
Okay, so it will be that many number of dimensional line.
Yeah, this S will be that vector in that multi-dimensional space, and the starting point is just a point in that multi-dimensional space.
Okay, sir.
So along this vector means up to 3 dimension we can visualize. Beyond that, it's difficult to visualize.
Sir, and also, what if the optimizing function is not a circle?
Yeah, it could be anything, no? So this could be log of x3. It doesn't matter, no? You will get some log of after transformation. You will get log of some alpha.
Okay, sir.
So as you can observe here, this the transform function, the alpha function will be always a linear quantity. Whatever it is, since we are using numerical method, so means we are not worried about differentiation and other problems in this particular case. It will be differentiated. Even if that function comes very complex in terms of alpha, what we are going to do is f of x plus h minus f of x divided by h. So we have to just evaluate whatever that complex function twice at two nearby points and calculate derivative. Even if you have to calculate derivative. If you are using direct search method, then you have to just keep on calculating.
Yes.
So if your worry is that we will land up in a function which is very complex in terms of alpha, it doesn't matter for numerical method, in the sense, supposing you are having sufficient computational power.
Okay.
As far as writing program is concerned, it doesn't make any difference. The complexity of function doesn't matter. Okay, so once we have done this, then means actual calculation, I'm not, for the sake of time, I'm not writing down the entire calculation, so that maybe I will circulate my calculation. So second part is you have to now locate where the minima would lie along for this function. So now we will be concentrating on this function. So part A is what we just now did. This is part A, where we develop the multivariate function into a univariate function along a search direction. So part B, we will use the exhaustive search method to bracket the minima. So along this line, with this as a starting point, where would be the minima, one would do that. So what calculations which I will circulate later. So I'm assuming that initial guess. So for exhaustive search, you require only initial guess. So alpha 0, that is the first guess I'm keeping as 0. And the increment in alpha, which you require for the exhaustive search, means you will be dividing this into number of equally divided points in order to locate the minima. So delta alpha I kept as 0.5. So both of these are assumed arbitrarily. So once you proceed that, you will find that the alpha value indicates this particular thing. After doing the calculations, the intermediate steps I have not given. It shows that the alpha, the minima lies between 1.5 to 2.5. So we got a rough idea as to where the minima would lie. And then part C is where you will be using one of the accurate methods. So here one could use the golden section method, or one can use the bisection method. So whichever method can be used to, so here I have used the golden search method to calculate the minima point. To find minima. So in the golden search method, the initial point is 1.5, the final point is 2.5, and epsilon, which is the tolerance that we are, or the termination condition we are using, is 0.1. So again, the steps I'm not giving, I'm just giving final result. So using this method at the end of my termination, I get the minimum value, or rather alpha value I should give. So the alpha star, that is the minimum along this particular direction, we get as 2.129, which we now again unfold into its original variable. So we'll calculate using this alpha star, we can calculate what is the x1 star, which is 2 plus 2 alpha, which is equal to 6.258, and x2 star is 1 plus 5 alpha, that is 11.645. So note that this is, we already know that the minima is at 10 comma 10, but note that this, we are not started in, we are started in the direction which is which will take us only to the nearest to the minima point. or hopefully nearest to the minima point. In this case, because of the nature of function, it will take us to the closest point along this line to the minima, and that is what we have obtained at the end of this process. So in the next iteration, you have to take this as the starting point, whatever we have obtained. So this point as a starting point. So in the next iteration, this x1 star and x2 star will form the new starting point. Again, you have to search new search direction and then repeat this procedure till the time your termination condition is met. So this is how this particular unidirectional search method works, by converting a multivariate problem into that of a single variable problem. So any questions on this? So next we are going to cover the more numerical methods, which are, so let's go back to our starting point. So we are now into this multiple variable type. So we have seen one method which is a univariate type. Now we'll in the remaining part of the session, we are going to see two more methods, which are based on one method based on direct search for multiple variables, and another is gradient based method again for the multiple variables. So each of these two methods we are going to see. So as it is a long session of 2 hours, we'll take a short break of few minutes, maybe 2-3 minutes or 5 minutes before we proceed next. So you can just wash your eyes if you are feeling sleepy, or if you have already slept, then you can wake up. Okay, so I'm just pausing for 2 minutes. So it is 2:57. So we'll restart at 3 o'clock, or 1 minute past 3 to be exact. Okay, so let's restart. So anybody has any question till now, whatever we discussed? Okay, so let's proceed with another approach for solving multivariate problems. So in multivariate problems, one of the strategy for searching can be explained as follows. So again, we'll take two-dimensional problem as starting point. So you have some function of objective function involving two variables, and the objective function is as shown here, and you have taken a starting point at a particular location. So this direct search methods, they depend on, or they begin with a starting point location which is randomly chosen. So once we have chosen the point, in the earlier method we have decided which direction to search for and then move ahead. In this particular case, what you do is you change each of the variables. So in this case there are two variables, x1 and x2. So with respect to the starting point, you move forward and backward in x1 direction. So you have these 2 points, and at the same time simultaneously you also move in x2 direction in forward and backward direction. So as a result of this, you will get 4 points as the candidate points. So since we are moved, let's say x1 you are moved in positive direction and y1 also in positive direction, so we'll reach a point which is this one. So this is a new point. And similarly, if it is x1 is negative and x2 is positive, then you will reach another point, then third point, and then fourth point. So in this way, by moving by certain distance, let's call it as delta, in either directions, you will reach you will reach a set of 4 points which will test for being minima. So in this particular type of or family of algorithms, from a given starting point, you generate points which are surrounding this your region, your starting point, and each of these point you test them whether they are having function values smaller than that of the starting point. If it is smaller than starting point, the smallest point becomes the new starting point, and this process repeats. So for example, in this case, you apply this particular procedure, you get 4 points, you evaluate the function value at these 4 points, and you observe that this particular point is having the minimum value. Then you will consider this as the new starting point, and then you will generate another set of points around this point. So at this point, you will again generate the 4 points. So those 4 points would become as this. So this is, in the second iteration, you will get 4 points which are as follows. So something of this type you will get at the end of second iteration. So with this set of 4 points, again you find out whether the 4 points are close to the minima. So assuming your minima is somewhere here, you will find that none of those generated 4 points are the minima points. The original point, the starting point itself is having minima value. So in that scenario, what you have to do is you shrink the size of your generation logic. So originally you had certain value of delta. When you found that with that delta you are not able to capture the minima remains the same, the starting point, then you reduce this delta and you start creating your box which is smaller. So in that case you will find 4 points which are now shrunk closer to the starting point. And out of this, then you will find that the minima has now shifted to a new point. And this procedure you keep on repeating till the time you reach the minima. So the procedure what we did here, it can be extended to any dimensional space. So for 2 dimensions, you require total 2 points. That is for two-dimensional case, two-dimensional problem. We require total the function evaluation needs to be done, or the points which are to be evaluated for minima are 4 plus the original point, that is 1. So if it is n-dimensional space, then how many points do you require? Obviously you require 1 point, the starting point you have to evaluate the function. But what would be this number? I repeat the question that if it is a two-dimensional space, then we are generating 4 new points, and that is where you are evaluating the function. Plus 1 is the starting point itself, is where we are doing evaluation. If it is an n-dimensional space, so if, for example, if it is a 3-dimensional space, how many points you will require? Rather, you will generate
The n square number of points.
Okay, is it n square?
It's a 2n.
2n.
What is that?
It's 2 power n.
2n.
2 power n. So that's right. So it is 2 to the power n is the number of points you are generating. So in every dimension you are generating 2 points, and you have to combine. You require combination of all those 2 pairs. So that becomes 2 to power n in n-dimensional space. So which means that this particular method is called as it's very simple to implement, and it was developed by a person which is whose name is box. So although this algorithm visually represent a box, so that is just a coincidence, but the person who developed this is known as his name is box. So that is known as Box's evolutionary optimization method, and it works with the logic which I just now explained. So in this method, you have to evaluate the function at every turn at 2 to power n plus 1 points. So that is the computational load this particular method is there. So the other methods which are there in the direct search method, they vary in terms of how much computational load is there. So for other methods, you may require some of the methods will require lesser than this type of evaluation. So in that sense, they are better. But each of these method have some advantage and disadvantage, and that can be seen in the textbook. So, but this boxes method is good, and it works for many of the practical problems. It has been applied to many practical problems and is found to be giving good results. The logic I have already explained to you. So you start with a starting point and this distance delta, and then you keep on finding the new points. So these new points which are formed around this point, so the name which this algorithm gives to this set of new points, so they are called as the hypercube corners. So cube, because this particular box has got an equal dimension in all particular space, which is not essential in the sense this delta along x1 direction and delta along x2 direction, they could be different. It is not essential that delta 1 and delta 2 should be same. You can choose any different values in different directions for spacing of the points. But if you are keeping all dimensions same, then it will have in 3 dimension, you can visualize this set of points as the corners of a regular cube. In 2 dimension, it is the corners of a regular square, and in high dimensions, it is the corners of the hypercube. So that is what just a term that you should be aware of. So you come across this particular method, you will have a term called as a hypercube. So that is nothing but if you join all the corners, then you will get solid which is the hypercube. Okay, so now let's write down the steps so that this particular method can be implemented as a computer code. So step 1, choose an initial point x0 and size parameter or parameters delta I for all design variables I equal to 1 to n equal to number of variables. So in general, this whatever I wrote here delta, this is same as delta is written in this algorithm. So this delta I means delta 1 is the distance by which x1 is going to vary. Delta 2 is the second variable is going to vary, and so on. So you can keep them same or you can keep them different. Then set x bar, that is initial starting vector, as x0. So that is the starting point of this particular iteration is x0. That is the starting point itself. Then step 2. Okay, and you have to also choose a termination parameter. Epsilon. So this termination parameter is the size limitation restriction on the point. So as you proceed in this direction, the size of the hypercube is going to become smaller and smaller. So whenever it meets your condition that within the tolerance that it has become, let's say 0.001, the size of all this hypercube, then you will say that you stop at that particular point. So in general, since all dimensions need not be equal, so where to apply this epsilon could be a question. So in that case, we calculate this as if magnitude of this delta vector becomes smaller than epsilon, then terminate. So this magnitude is nothing but under root sigma delta I square. So whenever this magnitude becomes smaller than epsilon, then you stop this particular thing. So this magnitude is this one. Else, if the termination condition is not met, create 2 to the power n points by adding and subtracting delta I by 2 from each variable at x bar. So okay, so just one correction here with respect to whatever I talked. So here we have taken delta and delta. So here delta I is total of this. So this total is delta I. So we are going delta I by 2 in the forward direction, delta I by 2 in the backward direction. And step 3, compute function values at all 2 to the power n plus 1 points. Find the point. So all the hypercube corners and the starting point, you calculate the function values and find the point having minimum function value. and designate the minimum point as x bar. So x bar is now your new starting point. So after this, you will be going back to your step 1. But before that, you have to do one check. That is, x bar happens to be same as your previous x bar, then you have to take some step. So that's what you are going to check. Otherwise, you will never going to find any minima. You will remain at that point only. So step 4 is crucial, where you are going to change the direction and the dimensions of this hypercube. So if f of x bar is same as f of x naught, that is the previous starting point, reduce the size parameter. So delta I would become delta I by 2 and go to step 2. So here delta I equal to delta I by 2 is one way, but you can reduce it by any proportion. So depending on your problem, one can set this reduction parameter to other than half. So in this case, I just, for the sake of as a average case, not average case, but as a just simple intuition, if no knowledge about the behavior of the objective function is known, then you will keep on halving this size parameter in each of the iteration. So that is what has been done, but that is not important. It could be done otherwise. Else set x naught equal to x bar. So x naught is the initial point. So that has to be set as the point where the minima is found, and go to step 2. Okay, so is this procedure clear? I think we discussed, let me illustrate it with an problem. So we'll take some numbers and illustrate how it proceeds so that it becomes clear. Any question at this point? Okay, so let's proceed. So example, minimize fx bar equal to x1 square plus x2 minus 11 the whole square plus x1 plus x2 square minus 7 the whole square in the interval x1 greater than equal to 0, x2 smaller than equal to 5. So that is the problem. So this is a function of two variables which we have to find the minima. And although we are discussing unconstrained problems, so here in order to choose the starting point, you have been given some directions that x1 should be positive and x2 should be less than or equal to 5. This particular function that what is shown here, so that is some specific function. So there are some set of functions which are known as testing functions. So they are these testing functions are used to check the performance of optimization algorithms. So once you have developed your optimization algorithm, in order to test how does it perform, one applies that algorithm on certain set of standard testing functions. So the function that you see here is one of such testing functions. The name of this function is HiMeBLEU function, HIMMELBLAU, HiMeBLEU function. This particular function, it is used for testing, so that you can compare the performance of two algorithms, how it behaves for this particular function. So this you can get more information on Wikipedia of once you put MLB function, you will get it. And along with that, other testing function information also you will get. This particular function has got local minima. So it has got multiple minima. So that is why it is used as a testing function. So whether your function, how fast it can reach to one of the minima or all four of the minima. So the local minima are four in numbers, and they are as follows. So x1, x2. This is just for information. This is not part of the problem, because this particular function we are going to use for other cases as well. And f minimum is 0. So one solution is x1 equal to 3, x2 equal to 2, and function value for this is 0. The second is minus 2.8051, 3.1313. Again, it is 0. Minus 3.7793 and minus 3.2832. Again, it is 0. And 3.5844 minus 1.84810. So these are the four minima that this function has got, and it has also got a local maxima. So this function can be tested for minimization problems as well as maximization problems. So that is at minus 0.2708 and minus 0.9230, and f max is 181.617. So in case you are just playing with some of the code and you want something to test with, then this function, and from internet you can obtain many similar set of functions which are having different properties, and the performance of your optimization code can be tested against this function. So the same MLB function, one of those functions is MLB function, and which we are going to test, which we are going to use that to find the minima using the boxes algorithm. So of course the full algorithm can be run with the computer code. Here we'll be looking at some of the steps. Yeah, so step 1. So first step is to choose the starting point. So that can be done randomly. So here I have chosen the starting point as 1, 1. And the size parameter, that is what should be the dimensions of the box along each direction, I have taken 2, 2. So that is the, in x1 direction it is 2, and x2 direction also it is 2. And epsilon, which is the termination condition, is taken as 0.001. So the first step of our case is you have to set x1 equal to x bar equal to x0, that is a starting point. So we are going to do that, and then we are going to check whether the size is less than epsilon. The size of the hypercube is less than epsilon, and then we are going to create 2 to power n points. So in this case 2 to power 2, that is 4 plus 1 including the initial point. So total 5 points we'll be evaluating. And how these points are generated? They are generated by adding and subtracting the delta I by 2 from each of the variables. So that is how these points will be generated. Then we'll compute the function value at all these points, and we'll evaluate what is, if there exists any minimum point other than the original point, and then we'll take decision accordingly. So let's proceed with the calculation. So step 2. So in the step 2, we'll calculate the magnitude of our size parameter. So that is 2 square plus 2 square. So it is 2.828, which is obviously higher than epsilon. So which means that we have to continue. Otherwise, if the hypercube size is small than the termination condition, then we have to stop there. So we create a hypercube around x bar equal to x naught bar, that is 1 1. So we'll get 4 points. So x naught is the original point, and each of the corner will have a point number. So you'll have second point. I'm just writing in a specific manner so as to maintain the uniformity later on. So since it is a two-dimensional problem, you will generate 4 points in addition to the original point. So how these points would be generated is by adding and subtracting delta I by 2 from each of the parameters. So in the first point, I will be subtracting delta I by 2 from both the parameters. So it will be 1 minus 2 is the delta and divided by 2. So this 2 is coming from, so this 2 is this 2. And in the y direction, again it is 1 minus 2 by 2. So where the other one is the parameter in the other direction. Since in this case both are identical, so that is why they are becoming same. And this 1 and 1, they are coming from, so this one is this one and other one is the other one. Okay, so having understood this pattern, now we can tell the remaining points very easily. So in x2 point, I'm just adding one side and subtracting the other side. At third point, I'm subtracting from the first point and adding in the second point. And here I'm adding in both the points. So we get the first corner point as 0 0, the second corner point as 2 0, the third corner point as 0 2, and the fourth point as 2 2. So what we have essentially done is we started with a point 1 1. And around this point, we have created these 4 points, which are as shown here. So one of them is 0 0 and others are as follows. At each of these points, now we have to evaluate the function. So step 3 is we have to evaluate the function at all the points. So f of x naught is equal to 106. F of x1 is 170. F of x2 is 74. F of x3 is 90. F of x4 is 26. So we find that at f of x4, we are finding the quantity to be minimum. So that means this 2 2 is the point where the minima lies. In the sense, at this iteration, the minimum is found out to be at f of x equal to 4. So this is step number 3. So this is the minima, and that implies that the x bar would be equal to 2, 2. So that is the point where we have to test it whether this matches with our starting point. So step 4 is we have to check whether the point we have found, whether it's a new point or it is same as the old point. If it is the same as the old point, then you have to reduce the size of the box. Otherwise, you have to take that point as new point. So since we are having x bar not equal to x naught, therefore the new x naught would be equal to 2, 2. So after this, we have to again go back to step 2. So this is end of first iteration or first cycle of this algorithm. So in the step 2, we have to check whether the magnitude has become small enough. So in this case, the magnitude still remains same. So it is 2.828, which is smaller than epsilon. So that means we have to create the hypercube. With this 2, 2 as the central point. So from this point, again, you have to, from x1, you have to add, subtract 0.5 and so on. So we'll get the new x1 as 1, 1, the new x2 as 3, 1, x3 as 1, 3, and x4 as 3, 3. And we evaluate the function at each of these points in step 3. So we'll get f of x1 as, let me start with f of x0 as 26, f of x1 as 106, f of x2 as 10, f of x3 as 58, f of x4 as 26. So we got the minimum point as x2, where the function value is minimum. So we get this point as the new starting point. So which implies that x bar equal to 3, 1. Then step 4, since we have again found a new point, so it is not same as the original point. So since x bar is not equal to x bar naught, therefore the new x bar naught would be equal to 3, 1. Okay, so this becomes sort of means just to look at this at the board is sort of boring, but that it cannot be helped. So so we are back. The second cycle is over. Now we are going to third cycle. So in the third cycle, we are getting x. I just want to demonstrate that point we will reach where the box size has to be reduced. So that is what I'm trying to do. So it is 2, 0. X of 2 is 4, 0. X3 is 2, 2. And x4 is 4, 2. And corresponding function values I will just write below this. So the function value, so f of x naught we have previously calculated, so that is 10. And corresponding to each of these, I'm just writing the function values in the box here. So these are the function values. So corresponding to x1 it is 74, corresponding to x2 it is 34, corresponding to x3 it is 26, and corresponding to x4 it is 50. So in this case you observe that the minima is 10, that is same as the original point we started with, so the original point does not change. So at this stage we will have to change the size of the box. So the step 4 would kick in here. So step 4, where we are testing whether the new point and original point is same. So this implies that the x bar would be equal to 3, 1. That is the same as the old point. And since x bar equal to x naught, what we previously obtained, therefore we'll have the delta bar as the old delta bar divided by 2. So this will become, earlier it was 2, 2, now it has become 1, 1. And then you have to proceed in the same direction. So that is how this particular solution works. So if you write a code for this, then you can find out that it will reach to the minimum point corresponding to 3, 2 with the choice of the starting point. So the choice of starting point will lead you to one of the minima point of the Himmel-Blue function. So that is how the boxes algorithm works. So any question or doubt on this algorithm? We are generating a number of points around the central point and testing whether the minima is anywhere away from the central point. If it is away from the central point, then that new point becomes the new central point, and again you generate new set of surrounding points, and you keep on doing this till the time none of the surrounding points become minima. So in that case, you shrink the size of the size parameter for generating the new points. So you start generating points closer to the central point, and again you test that, and you keep on repeating this till the time the size parameter becomes less than your tolerance. So that is, in summary, the box's evolutionary method. The term evolutionary in this particular algorithm could be misleading, because later on towards the end of this course we are again going to see something known as the nature-based algorithms or the evolutionary algorithm. So that is something very much different than this particular algorithm. So this algorithm has nothing to do with the more modern optimization algorithms, although this name given by the authors to this method is boxes evolutionary algorithm. So just those of you are thinking that this is a type of another set of algorithms called as evolutionary algorithms. Of course, we have not studied it, but you might have come across it through your general reading. So this is not the modern family of algorithms. This is relatively classical method, which works for many of the practical problems. That is very simple to implement. Only drawback of this particular problem, it does not guarantee that it will reach the minima. So it will reach a particular point which is closer to minima, but need not be essentially the minima point. So you may drift somewhere closer to the minima, and you miss the actual minima. That is, if the actual minima is somewhere here, and you have generated your 4 points closer, so you keep on coming closer to the minima point, but at one stage you may miss hitting the minima point, and then in that case the final point that you will reach may not be exact minima point, although it will be very close to the minima point. So that is the limitation of this particular method, though for practical point of view it is okay. And now we'll conclude today's session with the final topic, that is we have seen the direct search method. That is, the boxes method is a direct search method. It doesn't involve gradient. the multivariate gradient based method, there are again number of methods. So one which we are going to see is known as Cauchy's steepest gradient, steepest descent method. Cauchy's steepest descent method, that is what we are going to see. So multivariate problems. Gradient based method. And the method that we are going to look at is known as Cauchy's steepest descent method. So I see that some of you have already done some courses in Coursera or Swayam related to machine learning or otherwise. So you'll find that in machine learning, this particular algorithm, that is the steepest descent method, is very popular. So it is the machine learning problem essentially is at the core of it, at the heart of it is an optimization problem. So in order to reach the optimum problem, optimum solution, use the numerical method, and the Cauchy steepest descent method is something which is those who have done or are doing machine learning course, they would have already encountered this particular method. So this particular method, it is nothing but a variation of our first unidirectional method. So in the unidirectional method, we said that the direction can be chosen arbitrarily. So if you have to decide which direction to choose based on some knowledge that we had in previous lecture, maybe you can tell something. So can somebody tell if this is my objective function and I have decided some starting point, how can I decide which direction to start searching? There is some property which we discussed when we are talking about the analytical methods.
The slope would be the most negative.
Sorry?
The slope would be the most negative if we are moving to a minimum.
Slope, up to slope it is correct, but most negative is not correct. There is some property of, we are here in the multi-variable domain. So there the slope is replaced by gradient. So there is some property of gradient, which I think, yeah, I told that during the class. The direction of gradient has some meaning, physical meaning.
So the gradient points in direction of steepest descent, right?
Okay, anybody else? No, you are half correct or rather half incorrect. You're right that the direction of the gradient is along the steepest descent, but it is just along, whether it's towards the descent or towards the minima, or it is away from the minima. Means it is parallel to the direction along which the minima lies, but the direction of gradient is towards minima or it is away from minima.
So away.
Yeah, means now that I have said, yeah, that is yes, that's correct. Excuse me. Yeah, so the gradient direction yeah, excuse me. So gradient direction is towards the direction of increasing of the function. So that is the direction in which the function increases, and the reverse direction is the one in which which is towards the minima. So minus of del f is the direction towards the minima. So this is towards the minima. minima. So this property we use. So essentially this is just the univariate unidirectional method which we discussed some time back. It takes the advantage of the property of gradient, that negative of the gradient is the direction in which the minima lies. It need not exactly lie, like here the minima is here. When you start at this point, at this particular point, the gradient points towards the direction in which the minima, the opposite of the gradient points in the direction in which minima lie. It may not take you exactly to that direction, but that is the best possible guess you can make with the information you have at that particular point. So with having understood that, the later steps are just writing down the unidirectional algorithm that we discussed earlier. So step 1 is choose maximum number of iterations to be performed. So the termination condition could be based on the number of iterations, or it could be based on some termination parameter equal to m. So in this case, m is the parameter, the number of iterations. Then you have to choose an initial point. So this initial point usually is random, x0, and two termination parameters. So based on different criteria, that's why there are two criteria for termination in this algorithm. So that is why epsilon 1 and epsilon 2. And there is some counter k equal to 0 that we are mentioning here. So step 2 is calculate the gradient of function at point f of xk at x of k. So this k is the iteration number. So at the starting point, this k will be equal to 0. So x of k will be equal to x of 0. So that is x at the 0th iteration, and you calculate the gradient. Now, how does one calculate the gradient numerically? So the procedure remains exactly same as that in the single variable functions, except here that we have to calculate in the gradient, you are differentiating the function with each of the variables. So it is a partial differential that we want. So it is del f by del xi at any point xt that we are calculating. So this xt is just given to differentiate it from xk. So that t has no meaning as such, just to differentiate. So in this case, if you are differentiating with respect to xi, you have to just vary the value of xy, keeping all other terms constant. So it is f of xi t, that is the original point, plus delta xi t minus f of xi t minus delta xi t. And this whole divided by 2 delta xi t. Okay, so what we are doing here is that suppose we want to find out the slope of this any function, any arbitrary function fx at point x of t. So at this point, if you want to find out the gradient of a function, you require the partial differentials of this function with respect to each of the variables. So if you choose the variable as xi, then what you have to do is you have to calculate the value of the function considering only variation in xi value. All the remaining that is x1, x2, x3 except xi, all other will remain constant except this xi value will be changed. So change in the function when you increment it by delta x and when you decrement it by delta x divided by 2 times delta x. So this is a central difference method. So you can do it by forward difference method, in which case the second term to be subtracted will become the function value at xi, and this will become the function, the first term will become function value at the incremental or forward direction. So that is how you will calculate the gradient numerically. So you'll have to write a code which will generate this gradient vector, or it will be in the form of an array, and each pocket of that array would be this partial differential which is calculated numerically. Once we have done that, then step 3 is, so what you are doing here is that if gradient is near to the 0 or it is almost 0, then we have to stop there. So we need not go ahead. So here we are calculating what is the magnitude of the gradient at this particular point. Once you have calculated the gradient, you calculate its magnitude. So this is the magnitude of del of f, so which is under root each of its terms. So if it is less than or equal to epsilon 1, which is the first termination condition, then you terminate. Then you stop because you already know that gradient is small enough, so you need not proceed further. Else if the iteration, so if the k is the number of iteration, if it is greater than or equal to m, then also you terminate. So note that I'm giving the code which can be just converted into programs. So otherwise, for human reading, these steps are not required. Else go to step 4. So you have to go to next 4 if your gradient is not very small, or if the number of iterations are not exceeded your limit. So step 4 is perform. So here the entire unidirectional algorithm has to be inserted here. So perform unidirectional search to find alpha k using epsilon 2 as termination condition. For minimization of f of xk plus 1. So you convert your original function into that of means now you have the search direction s bar, and you know the initial point x naught. So you can convert means each of the variable x1, x2, x3 you can write in terms of the single unknown alpha, and then find out the value of alpha which will minimize this particular function. And for that epsilon 2 is the minimization condition. And step 5, once you have done that, then you will get your new point x of k plus 1. So if the magnitude of x k plus 1 That if you subtract the original vector and the new vector and its magnitude is smaller than the magnitude of size of the original vector. So if it is less than your termination parameter, then you terminate. So one is condition based on gradient. So if gradients become sufficiently small, then you terminate. Or other is if the difference between the new point and the old point. So this is nothing but the distance between the old and new point with respect to the position, means the distance of that point from the origin. So if that becomes small enough, then you terminate. Else you start a new iteration. So you increment k by 1 and go to step 1. Step 2. That is where you are doing the calculations. So that is how this particular Cauchy Steepest descent method would work. So this means doing manual calculation is of no point. So maybe we can cover this in one of the assignment to understand how it works, or better I will give this as a part of your project. So in this week I will issue your first course project in which you have the opportunity to apply the methods. So we discuss different types of methods. So you have opportunity to apply different methods and see how they behave for a particular case. Okay, so we'll stop here for today. And if you have any questions, then we have a few minutes to discuss that. Anybody has any questions? Okay, one thing is I am not sure of behavior of my attendance plugin because Google has changed something. So it shows some people absent. I just want to confirm that. Okay, so all of you, can you just write present in the chat box? Just type in present in the chat box so that I can confirm. Okay, in my plugin, it is showing me Mukul Achwala is absent and Shitika Gala is absent. So are they there or they are not? I can see their balls. So Mukul, are you there?
Yes, sir.
Yeah, he's there. So some glitch in the software. Shitika, are you there?
Yes, sir.
Okay. I don't know how to abandon using this extension. Anyway, so thanks for your time. If you don't have any question, then we'll stop here.